Welcome to CS3308 Information Retrieval. This is the Unit 4 lecture part 3. In this lecture we're going to talk a little bit about the vector space model and cosine similarity, and to give you some context to that, if we go back to the first lecture, what we talked about was the need for ranking retrieval because the Boolean model oftentimes doesn't work. And so we wanted to have a ranked retrieval model, something that could kind of look at the terms and find the things that were most relevant and order them in terms of relevance and then return them a few documents at a time so that we can actually make use of it. We looked at the Jaccard coefficient as one way of determining that relevance, and basically with the Jaccard coefficient we looked at the query terms, and we looked at the document as a set, and we looked at the intersection of the two, and we came up with a way of dividing the number of terms that were in the document, the intersection point, with the number of terms in the entire set. We found that that wasn't a good way of doing it because some documents are very large, and so the denominator was very large, and that would skew the results. The second lecture, we got into looking at a different way of doing this, which is to use the term frequency and the inverse document frequency. If you recall, the inverse document frequency looked at how frequently a particular term appears across the entire set of documents that we have in the corpus. And this was a weighting factor, and then we multiplied that times the frequency of a particular term as it appeared within the document, and this gave us a way of ranking or calculating a relevance level of a particular term as it related to a document. Now in this lecture, what we're going to do is we're going to look at how do we take that term frequency, inverse document frequency measure that we calculated, and how do we use it. So the first thing we need to explore and think about is this concept of a document as a vector. Now, I just wanted to go back and kind of draw you a graph here. So imagine, if you would, that we have a traditional graph structure here. And normally what you'd do is we'd have this thing and we'd label this as y and we'd label this as x. So if any x y pair that I calculate, such as 0, 0, it represents a point on the graph. And essentially this is how I would plot a point in 2 dimensions, right? And then perhaps we could have a 1, 1, which shows up at this point, 2, 2, which would be out here like this. Maybe I have a 3, 0, and that winds up being here, right? So basically the idea is that any couple of numbers, I can actually plot them in this graph, and this is kind of what we call Euclidean space. And we know the x factor, y factor, or the x dimension and the y dimension calculates or defines a 2-dimensional space, and then I can actually add the 3rd dimension, which is z. Beyond this, and by the way, we can go beyond this, but beyond this I can't really write a graph to do it, but we do know that we have this concept of v-dimensional vector space. So I could have many, many, many dimensions and plot points on those dimensions. So the basic idea here is terms become the axis. Instead of using x and y, maybe I would use terms such as home and mortgage. So if you think back to our calculation of the TF-IDF, basically what we did is for any term in a particular document, I would calculate a weight, and that weight I could then plot on an x, y, z, etc., etc., etc. But let's just use home and mortgage x and y basis. So for example, maybe my x value for home was 1.5, and my y value was let me see, 1, 2, 3, 3. So this would be a xy of 1.5, 3, and that would represent the TF-IDF of the x, which is home, and the TF-IDF of mortgage, which is 3, or which is y, which is home, which is mortgage here. I'm sorry, with a value of 1.5 for the x dimension and 3 for the y dimension. Again, this 1.5 and 3 is the TF-IDF that I calculated for each of these terms for that particular document. Now, the other thing I wanted to mention is the fact that the query itself is a document. So when I put a series of terms together, so maybe I put the term together home mortgage, this becomes a document. And I can actually calculate the TF-IDF on each of these terms. Now, there's only 2 terms in the document, right? So n is only, number of documents is 1, number of terms in the document is 2, and the frequency of each term is 1. So essentially, it's a very simple thing to calculate, but essentially I am going to be able to calculate a vector for each of these. Okay, so wanted you have this kind of concept because of the fact that I can have millions potentially of terms. I can literally have potentially millions of dimensions in the model that I calculate. We're only saying 2 here. We could add the third one visually, but beyond that we can't do that. So let's think about queries as vectors. We just kind of talked about this. The query itself, or the terms in the query, is a document. So I can actually calculate the TF and IDF for a query. And then the basic idea is that I can actually use this ability to take terms from a document and the terms from the query and calculate them. So for example, perhaps this is the position of the query, and this up here is a position of document. Let's call that document 1. This perhaps is a position, we're going to call it document 2. So now I've plotted this. One of the things I could do is I could say, well, maybe the way to determine similarity is by looking for the plotted points that are closest to the query. Pretty cool idea, right? Well, it's one way of doing it. It's kind of a first cut. We could look at it and look at the distance between the 2 points. By the way, there's a machine learning algorithm that's called K nearest neighbors. And basically what K nearest neighbors does is it actually goes out and it calculates these points and finds the ones, K being you pick some value of K, maybe 4. It'll find the 4 documents that are closest to the query document, right? We could use that algorithm and actually do this. Now the problem is that since we're using Euclidean distance, it tends to not work out very well for us. And one of the reasons why is because that distance, the difference between it can actually get pretty large for vectors when they're different lengths. And let me explain what that is or how that works for you for a moment. You kind of see this looks like the document that we did. This would be our query terms, right? We plotted it on our XY basis. This would maybe be one document, this would be another document, and out here I have a third. And the reason for that is because the length may have an impact on the actual position, right? So I might have something that just simply because of the number of terms in it. Now, keep in mind, I don't have to match all the terms. Maybe I have one document that has many terms, and because of the many terms, one of these dimensions is skewed way out here. So what happens is that this doesn't become such a good measure simply because the number of terms in the query might actually get skewed. Okay? So Euclidean distance doesn't usually yield a really good approach. So what do? What if we were to use angle instead of distance? Okay, and think about the problem here for a moment. Let's take some document D, right? And let's say that document has 100 words in it. Okay, now if I were to take the entire contents of that document and append it to itself, I now have a document that has 200 words in it. Now, each of those 200 words, or the second 100 words, is exactly the same as the first 100 words, so it means that the actual content of that document is exactly the same. Semantically, it's identical. However, the Euclidean distance between these two documents, because of the fact that one is twice as large, may be significant. We don't really want that to happen because the reality is that semantically, in terms of the meaning, the content of it, it's exactly the same. So Euclidean distance, as a rule, isn't going to work all that well for us. Now, what if we were to use angles? When I'm starting to use angles, the distance doesn't matter. Now, what do I mean by that? Now, imagine that this was our query terms. And imagine that D2 represents that document that actually has the 200 words. Now, the version of it that had 100 words might be plotted here. The version of it that had 200 words might be plotted here. If I were to look at the angle between the query, which is this one right here, And the document, it's relatively small. This angle here is quite a bit larger, as is this angle over here. Okay, so this is maybe angle 1. This one would be angle 2, and maybe this is angle 3. So each of these are different angles. So you can see if we're actually measuring the angle, this length, this distance doesn't really matter. So basically the idea is we're going to want to use angles. And one of the things, and I'm just going to pop back here again, is when I measure this distance right here in an angle, so kind of looking at this where I'm moving around clockwise and I'm measuring the angle, essentially what I'm looking for is I'm looking kind of for the inverse of the sine. So what does that mean? So if you think about a typical angle, and say we're starting at 0, it tends to move upwards, right? So that the angle is actually increasing. What we're looking for, and what we really want, is the smallest one, right? So I want the kind of the inverse of sine. And for that reason, I basically convert it to cosine, because as you can see, cosine basically is starting at the high point and it goes down and is decreasing in size. So this one increasing, cosine decreasing. So what we tend to want to do is we want to take the angle and we want to invert it. We want to convert it into a cosine because it's in decreasing order. Therefore, I have it automatically ordered such that the most relevant ones appear first. So basically what we do is we use something called the dot product on the vectors to calculate the cosine coefficient of the document. And basically Q, as you can see in this particular case, is the TF-IDF weight of term I in the query, and D is the TF-IDF of the weight of the term in the document. And again, so for example, if I had 2 terms in the query, home mortgage, I only have to add up 2 of them, right? I might have multiple terms in the document, but essentially it plots a vector. Okay, and so you kind of look at this again. It's the delta of the angle in here, and that's basically what we're measuring. So in our in the model that we're going to be creating, what we want to do is we're going to actually create vectors, which means we're going to plot the point, and then that's going to form a from the origin to the point is going to form a line. That line we're going to assume to be an array. It's a vector that extends out forever. And then what we were going to do is we're going to actually measure the angle of the distance. So the smaller the angle of the distance, the more relevant it's going to be. Does that make sense? And just kind of give you an example of this, we're doing it with just a couple of documents. Basically note that to simplify the example, we're not going to do all the TF-IDF weighting, but it helps you just get a sense for this. If we look at a term such as affection and Sense and Sensibility, all 3 of these are classic novels. We have Pride and Prejudice and we have Wuthering Heights. So the term affection appears 115 times in Sense and Sensibility, 58 times in Pride and Prejudice, and 20 times in Wuthering Heights. So, you know, the question then becomes, how relevant is affection, right? How relevant is jealous? How relevant is this term gossip? And we can kind of see that we can calculate these values, and then I can compute the cosine on them in this way. So any 2 documents, so in this particular case, the cosine coefficient between Sense and Sensibility is relatively high. It's much more higher than between Sense and Sensibility and Wuthering Heights, and between Pride and Prejudice and Wuthering Heights. So essentially, I would calculate these values. I would order them in decreasing order because the largest value means it's the most similar one. So hopefully you have this idea. The way that we're actually going to do our retrieval system is we are going to define the vectors. We're going to calculate the cosine coefficient on it, and we're going to do that by using the dot product equation, okay, of the vectors. And then we're going to order that in decreasing order. So the ones that have the highest cosine coefficient, those are going to be the most relevant ones. So I'm basically going to want to sort these in decreasing order, and then I'm going to return them in that order. So that's actually how my search engine is going to work. So just kind of a summary of the whole unit. Really, some of the key ideas is representing a query as a TF-IDF vector, because it's a document and I can calculate TF-IDFs on it just as I can for any other document. Again, we're going to represent each document as a weighted TF-IDF vector. And we've talked a little bit in the previous unit as to how we actually calculate what that is. We're going to calculate the cosine similarity score for each query using the dot product calculation. Okay, and we're going to rank all of the documents with respect to that score. So the higher the score, 0.94 would appear first, 0.82, and so on and so forth. So whatever that score is, we're going to have it in decreasing order. And then I have this concept of K. So maybe I'm going to return the first 10 or 20 of the results to the user so that I don't have an unmanageable search system. And that gives us a really good understanding of how a search engine works.